Hey guys, today we're going to be talking about conjugates. Part 2, what is the conjugate of a complex number? And I'm currently making a complex numbers series, and you are currently in the middle of the series. This is part 2. And if you want to start with part 1, in part 1 I just talk about what is a complex number, and we do a few examples of the imaginary number. And I feel like that you need to watch that video to understand what a conjugate of a complex number is. But if you're pretty much alright with complex numbers, you know their form, you know if it's purely real, purely imaginary, then yeah, you can continue watching this video. But if you are not sure, I suggest you go watch that video right now. Alright, let's dive right in. If z, which is a complex number, is equal to a plus bi, the conjugate of z would be z equals a minus bi. And this is how you represent a conjugate of any number. It's just z with like a kind of dash on the top. So the conjugate of this complex number would be this. And you see that there's not really much of a difference. It's a simple concept to wrap your head around. It's just that you swap the sign. So instead of plus being over here, it's a minus over here. That's pretty much it. So let's go through one or two examples of trying to find a conjugate of a complex number. Alright, so we have these three problems, and if you want, you can pause the video and attempt these three problems. And, yep. Alright, so I'm hoping you attempted these problems. If not, and you got a little stuck, that's okay. So following this rule, if z is equal to a plus bi, the conjugate of z would be z equals a minus bi, and z with a dash above. So, this problem. 3 plus 4i, what's the conjugate of that? Well, the conjugate of this, well, if this is equal to z, and this is equal to z, and this is equal to z, then the conjugate of this, you would just flip the sign. Instead of a plus, it would be a minus. So it would be the conjugate of z would be 3 minus 4i. And that is our answer, nothing more. Now off to this one. Z equals 7 minus 16i. Once again, you just swap the signs. So it's minus here, then our conjugate will be 7 plus 16i. So kind of the opposite of what it says here is you just flip the sign. If it's minus, then the conjugate will have a plus in it. If it's plus over here, then the conjugate will have a minus in it. Now, this one. This one might have been a little bit tricky, but nonetheless, it's still the same, except this time I want you to have I in the answer. So how do we approach that? Well, this square root 47, we can't simplify that, so let's just write square root 47. We can split this square root negative 19 into square root negative 1 times square root 19, because you just multiply whatever's in the square root. And minus 1 times 19 is minus 19. Then you see that, oh, okay, we have a square root negative 1. We know that a square root negative 1 is I. I is equal to the imaginary number, which is square root of negative 1. So this is still z, so z is equal to square root 47 plus square root 19i. Then it's just a matter of switching the sign. So that would be, the conjugate would be square root 47 minus square root 19. And that would be our answer. Alright, so let's try this problem now. Z is equal to minus 1 plus square root 17i. So pause the video if you want to give this problem a go. Alright, so once again, we simply switch the sign. But just be aware, we don't switch every single sign. We only switch this sign over here. Like we saw above, only this sign is being switched. This a still remains the same. So it would be, even though there's a minus over here, a will always remain the same. So minus 1 is a minus square root 17i, because over here it's a plus and here it's a minus. So just to make sure, a always stays the same, just the sign of b changes. So if it's plus b, the conjugate will have a minus b, and if there's a minus b here, then the conjugate will have a plus b. So this would be our answer. Alright, since now we got kind of like a gist of what conjugates are and a few examples, let's move on to what are the properties of conjugates. And mind you, there are a lot of properties of conjugate. Not a lot, but maybe like 10, 11 properties. So I'm just going to go over a few of them, and I'm going to also prove that, okay, like this property is actually true for all like complex numbers and their conjugates. And next, I'm just going to just display all of the properties of conjugates. Alright, so the first property is Z double conjugate is equal to Z. And let's prove this. Let's assume that Z is equal to A plus BI. So then therefore, from what we learned about conjugates, we know that Z conjugate is equal to A minus BI. Now, there are two conjugates, so let's take the conjugate of this once again. And how we represent the second conjugate is just 2 lines. So the first conjugate is 1 line and the second conjugate is 2 lines. So now we are going to try to find the conjugate of this. Well, the conjugate of this is simply A plus BI. We just switched that sign. And what do you notice? Well, we see that this double conjugate A plus BI is equal to the original complex number we had, which is also A plus BI. Hence, this property is true for all complex numbers. Alright, so on to our second property of conjugates. It states that the conjugate of the sum of Z1 and Z2 is equal to the sum of individual conjugates of Z1 and Z2. So how are we going to prove this? Well, let's assume that Z1 is equal to A1 plus B1I. And let's assume Z2 is equal to A2 plus B2I. So let's start with the left-hand side. We know that it's conjugate of Z1 plus Z2. Z1 is A1 plus B1I plus A2 plus B2I. And that's conjugate. And that's the left-hand side. Now for the right-hand side. So the right-hand side is going to be conjugate of this. So that will just be A1 minus B1I plus A2 minus B2I. Now let's take a look at this left-hand side. Let's group these i's together. So that would be A1 plus A2 plus B1 plus B2I. So basically I just took the I out of these two terms and left these two terms untouched. And it's equal to that. So basically if we prove that this is equal to this, then we prove that this is equal to this. So that's what I'm trying to do. So we see that this is actually a complex number, right? We can assume that maybe this is like the ultimate A and this is the ultimate B. It would be A plus BI. So this whole thing is a complex number. And now we just take the conjugate of a complex number. We switch this sign to a minus. So that's A1 plus A2 minus B1 plus B2. And if we expand this, we get A1 plus A2 minus B1I minus B2I. And this indeed is equal to this, which is A1 minus B1I plus A2 minus B2I. Hence, this property is true for all complex numbers. So the third property we are going to prove is conjugate of Z1 times Z2 is equal to Z1 conjugate times Z2 conjugate. And how are we going to prove this? Once again, it's the same exact procedure. Let Z1 be equal to A1 plus B1I. B1I. Let Z2 equal A2 plus B2I. Now, let's solve the left-hand side. So that's Z1 times Z2. Z1 is A1 plus B1I times A2 plus B2I. And then let's solve this. So that's conjugate of Z1, which is A1 minus B1I, times conjugate of Z2, which is A2 minus B2I. Now let's expand this. Keeping that conjugate, we get a1, a2 plus a1, b2i plus b1, a2i plus b1, b2i squared. Let's expand our right-hand side. That's a1, a2 minus a1, b2i. Oops, where'd I go? Okay, that and that. Next, we have minus b1, a2i plus b1, b2i. Now what we can do, let's simplify this part. So I'm just going to keep all of this the same. So that's, actually, let me go over here. So that's still conjugate a1, a2 plus a1. Oh, on second thought, let's take the I from these two out. So that's plus a1, b2 plus b1, a2i. And I squared from part 1, we learned that I squared is actually equal to -1. So that's basically -1 times b1, b2. That's basically negative b1, b2. And let's take the I out from, we also have to, whoops, I forgot the squared over here. That's I squared. Once again, let's take this I squared as -1 because I squared is equal to -1. So we get a1, a2 minus a1, b2i minus b1, a2i minus b1, b2. So I'm just, you see that this is a complex number. These are the real parts, and this is the imaginary part. So if we take a conjugate of that, we get a1, a2 minus b1, b2 minus a1, b2 plus b1, a2 I equals this whole entire thing, which is a1, a2, and now we can take out the I from these two. So we get, let's take out the minus I. So we get minus a1, b2 plus b1, a2 I minus b1, b2. And hence this is proved. This is this and this, and this is this. So hence we prove that the conjugate of z1 times z2 is equal to the conjugate of z times the conjugate of z2. All right, so our fourth property is that z times the conjugate of z is equal to the real part of z squared plus the imaginary part of z squared. And I'm pretty sure you know how to solve these problems by now. Just assume that z is equal to a complex number in terms of a and b. And just prove that the left-hand side is equal to the right-hand side. So if you want, feel free to pause the video and give this problem a go. Alright, so once again, pretty straightforward. Assume z is a plus bi. Now I just assume z is equal to a plus bi. You personally can just assume like z is equal to m plus ni. It really doesn't matter as long as you know that a, b, or m, n are in fact real numbers. But that aside, we know that z is equal to a plus bi. Therefore, z conjugate is equal to a minus bi. So the left-hand side would be a plus bi times a minus bi equals, and then we have to determine this equals. We have to see if it's actually equal or not. So the real part of z, as we saw in part 1 of this series, is a. So that's going to be a squared. And the imaginary part of z, notice that it's z, not z conjugate, but the imaginary part of z. And z is this. So the imaginary part of z, it's b. So that's b squared. So now let's see if this side is equal to this side. So this is like, is it equal to? So I just put that, I just put that question mark. And now solving the left-hand side, we get a squared minus abi plus abi minus b squared I squared. Once again, we have to see if the left-hand side is equal to the right-hand side. This and this cancel out. We get a squared minus b squared I squared. Once again, we know I squared is equal to minus 1, and minus b squared times minus 1 is plus b squared. And does a squared plus b squared equal a squared plus b squared? Well, yes, it does equal. So therefore, this property is true for all complex numbers and their conjugates. On the screen right now are all of the properties of conjugates, and the ones underlined in black are the ones we proved. And hopefully when you were proving them, it wasn't too hard. Just assume z is like any number, any complex number, I should say. And just go on from there, see if the left-hand side is equal to the right-hand side. If it is, then it is true. Like, the property is true. And you can use it in other problems relating complex numbers and their conjugates as well. So some of the problems I just want to go over. I'm not going to prove them because if I proved all of these 10, 11 properties, we would be here for hours. But hopefully you got the gist of that. So one of the properties I want to go over is this. So basically what this is saying is that if z is equal to the conjugate of z, then z is purely real. And in part 1, we discussed purely real means that it has no imaginary part. So purely real are numbers like z equals 3, 1.5, negative 7.3. Numbers such as that, where it has no I, aka no imaginary part. So b in that case would be 0. Same thing for this part. If z plus the conjugate of z is equal to 0, z is purely imaginary. And you can try that out yourself, see if all of these properties are true. I'm hoping you come to the conclusion that they are true, because all of these properties, they are true for complex numbers and their conjugates. So yeah, I hope you guys learned about conjugates, what is a conjugate of a complex number, and got some first-hand experience on how to find the conjugates. And yeah, I'll see you guys for part 3.